In this presentation we will discuss about the systems and applications of integrated optical devices. So, I have put up a few points. So, we look at fiber optic communication systems, optical information processing systems, sensing, storage. These are the various applications that integrated optical devices are required. This is a simple example of a fiber optic communication system. In a typical fiber optic system, one of the important problems in communications right now is networking, not only long distance communication. Fiber optic links have been very popular. They are now a reality for long distance applications. You can go for high data rate communications of the orders of 10 gigabits per second. So, in a typical situation, there are several users, not only a single user, but there are several users. The information has to be exchanged across all these people and so on. So, if we are using fiber optic communications for such purpose, there is also a necessity to switch or communicate between different users. And so, we have this is an example of a system where you have several, say let us say 4 users. They receive signals and then the signal from one user has to be communicated to another user on. So, we have 4 input ports and 4 output ports, and that signal has to be routed or switched from any of the input ports to any of the output ports. In this example I have chosen the directional coupler switches, electro-optic switches we have seen earlier. As we know, the electro-optic switch has a configuration of an directional coupler. I will just write again. Okay. A directional coupler switch has got 2 waveguide directional couplers, and then you have the electrodes over that. And depending on the voltage that you apply to these electrodes, you can switch the signal from the one input port to another output port. We have seen that earlier in electro optic effect. So, when there is no voltage on this, you design it such that it is in the what is called the crossover state, and when you apply voltage to this, you can switch back into the bar state. So, crossover state with no voltage and bar state with a voltage of say for example 5 volts or 9 volts. So, this is a functioning of the directional coupler switch, and we can configure this to achieve a higher order switching like a 4x4 switching. How can it be done is what I am showing here. There is one additional feature which we have not discussed earlier, is that there are tapered regions. These directional couplers have to be tapered if you want to connect inputs and outputs. We need, of course, there is a tapering between these sections which we are ignoring at this moment for conceptual purposes, but in the practical situation we need to consider the coupling of light between these and then adjust the voltages or the coupling lengths according to that. So, for the time being we will assume that the functioning of these directional coupler switches is as discussed earlier. So, when a signal is input at any particular port, or in fact we have signals at all the ports and they have to be exchanged at all the ports. We can represent this by a matrix of elements. For example, let me say the columns and rows represent different input output combinations. Say for example, power coming from the first port to be routed into the first port, or power coming from the third port has to be routed to the third port, and power coming from the second port may have to be sent to the fourth port, and so on. Whatever combination is needed. Of course, all combinations are not possible, but let us look in a typical given situation. We would like to send the power from the third port to some port, let us see. So, for example, I would like to send signal from the third port to second port. So, what I do, I can switch, I can put this in the crossover state. So, that light coming at this will go into this port, or maybe let me, for the time being, let me say it bar port, bar state, third one in the bar state, the light goes back, and here also I would switch to crossover state, light goes into this, and I will retain this once again in the bar state. So, bar state for this, crossover state for this, and bar state for this will send the signal into this port. At the same time, I can think of sending the first one to last port. For example, I will put this in the crossover state, this is already in the crossover state, and this also I will put in the crossover state. So, what happens, the light from this will switch over into this, and once again into this and to this. So, we have seen the case where the light from the third port has gone into the second one, light from the first port has gone into the fourth, and by appropriate combination of these switches we can achieve whatever a particular matrix that is possible. Of course, you can work out with more complicated examples, and you can say that not all combinations are possible. This way you can achieve higher order switching by using 2 by 2 elemental switches. So, when you look at the technology, typically this is made on a lithium niobate crystal with electrodes on top is what is shown here. The input is through fibers, each of the fibers contain the data signals typically of the orders of 10 Gbps, and they are modulated, the signals are modulated at 10 Gbps. You have typically laser diode transmitters are used, and at the output you can, if you want to detect the signal directly, you can put the photo detectors, and of course many times most of the at up to 10 Gbps you can also use the direct modulation of laser diodes. We will assume that the signal is modulated in whatever format you wish, and typically dimensions, if you look at, as you know, the waveguides are of the widths are of the orders of 4 microns thick and about 2.5 microns depth, and the electrode voltage of the orders of a few volts, and the overall chip would come to 40 millimeters. One of the important feature that we know about the conventional integrated optical devices is these angles are very, very small. So, these angles are very, very small, typically of the orders of a few degrees, 1 or 2 degrees. So, when you cascade several such electro-optic switches, the length of the chip is going to be quite large, 40 millimeters. And as you know, the fibers are of the orders of the core diameters of the orders of a few microns, and the overall cladding size is quite large of the orders of 250 microns. So, this is about 9 microns. So, you can observe that if you want to couple the light into the chip, you need to have a spacing between the fibers of the orders of 250 microns. So, this is very large. So, as the angles are very small, the chip becomes very, very long, and across the cross sections you can calculate that if it is 250 microns across each of these 1, 2, 3, about 4 times, about a microns, about a millimeter is the size across, and about 40 millimeters is the size across. This is a technological problem which we will address later on in future. Functionally, it is possible by using electro-optic effect to achieve a 4 by 4 switch array. Just to mention, there are many other ways that switching and routing of signals is done in optical communication system without converting the electrical domain. For example, MEMS we will see in the next one of the classes in future. So, I will go to the next application. So, this application called optical information processing. This is based on the acousto-optic effect we talked about earlier. So, just to recall, there is an IDT pattern, acoustoptic cell shown here. It is a finger pattern like this, or maybe already connected is this side and this side, and a surface acoustic wave can propagate a strain wave, and which can create a grating on the crystal. That means the refractive index varies periodically, creating a sort of grating, and we have seen that the light could be deflected by this grating. The light incident says, let me say the, so the light incident on this could be deflected into some directions. So, this acoustoptic cell and the surface acoustic wave or the grating is created here. These are the lenses called geodesic lenses. You can take a slab waveguide and by proper stress impression you can create a lenses like this. We have not discussed lenses in this course, but you can expect like a conventional lens. These lenses also have the same properties like the focal length and so on and like in the conventional lenses you can use them to focus the beam and beam shaping and so on and so forth. So, the input lens would spread the beam across this grating, and the output beam will help to redirect the various components of the signal onto the appropriate output photodetector array. So, this is a configuration. I will call it as a as an application to a spectrum analysis. So, we have seen that the acoustoptic effect is dependent on the frequency of the RF signal, the pitch of the grating and so on are dependent on the RF signal, and let us assume in this example we will use a laser diode input coupled into this chip. Of course, you have a planar waveguide here on which you have made all these components, and the input light is spread across the grating region and is redirected into photodetector array, and we apply the RF signal to be analyzed to this IDT pattern. And this is not a simple grating, it has a complicated grating of some arbitrary shape based on the RF signal. So, you can say that this is superposition of several gratings. That means there are several frequency components, RF frequency components in this. Correspondingly, the grating that we create is a superposition of all this, and we can say that the behavior of this device will depend on the RF signal. So, it is possible to work out depending on the various components in which direction the light is deflected by the overall. So, we can expect that the output we can calibrate and we can work out that the deflected signals at each of these photodetector arrays can correspond to different components of the RF signal. So, if you have an RF signal something like this, you can expect and calibrate the output of current of the photodetectors in a similar fashion, and we can use it for RF signal analysis. So, the crux of the problem is the acoustoptic effect, where you create a grating, periodic variation of the refractive index, and deflect the light into appropriate output ports. This is a basic idea of the acoustoptic effect based spectrum RF spectrum analyzer. Then there is one more application that we can think of using a similar arrangement. We can also think of optical spectrum analysis. So, we will talk about optical spectrum analyzer. So, in this particular case we fix the RF signal of a constant frequency, and we know what is the pitch of the grating and so on, and we give the optical signal to be analyzed here as a modulated onto the laser diode, or we can also say this is a composite optical signal of having different colors or frequency components which need to be analyzed. Intuitively or conceptually we can think of this optical signal to be various components of the optical signal to be deflected by this grating into different output ports. As we know, the grating has got a very good dispersive properties for optical signals, and we can use this property of the grating to create what can be called as an optical spectrum laser. So, technology wise we have seen that lithium niobate is a good candidate for acousto-optic effect, and we have used conventional integrated optical elements like the gratings, lenses and so on to achieve this. Once again we can note that the chip is quite thin across the dimension and quite long. This is one of the important directions that optical integrated optics has taken. The conventional optical elements like lenses, mirrors, gratings etc. have been translated onto an integrated optic form to achieve the conventional and new functions and also modern functions like the spectrum analysis, and also people have also tried to imitate whatever is in the electrical domain like the electronic switches etc. into optical domain. This is one of the important domains of classical integrated optics. When we go into the future we will see some modern devices which can do functionally different functions in a different way. So, completely new ideas could be explored to achieve various functions that are required in modern applications. So, we will go to one more application. So, this is actually in this particular example I am using this integrated optical chip for a sensing application. In fact, the chip itself is not a sensor, but is a support for sensor. Just let me give a brief intro to the sensing applications. I will take an example of a gyroscope, or I will just take an example of a gyroscope and explain what is a sensor and then how the integrated optical chip is being used for sensing application. So, in a fiber optic gyroscope you have a coil of optical fiber, several rounds, and you launch the light in the clockwise direction and anti-clockwise direction. So, this is typically a 500 meters length of optical fiber. We can calculate what is the delay that it can produce and so on and so forth. I am not going to details of the gyroscope, but just to emphasize that the integrated optic chip can be used for gyroscope application. I am emphasizing only on the function of this chip as well as the gyroscope. So, in a typical fiber optic gyroscope you have a optical signal going in the clockwise direction and counterclockwise direction, and they are superposed at this coupler, and the phase difference between these two elements delta phi clockwise and counterclockwise beam can be shown to be proportional to the angular velocity of the coil if this put it on a rotating object. Suppose this entire device gyroscope is put on a aircraft or a satellite, we can measure what is the rotation rate of this object. So, I am not showing you the calculations, but we can go of the orders of a few degrees per hour. So, to get an idea, you know that earth rotates in one day 360 degrees. So, the rotation rate of the earth is about 15 degrees per hour, and now in the current technology we have fiber optic gyroscopes of the orders of a few degrees per hour even fraction of degree per hour also available now. So, now I would like to emphasize in this application the role of the integrated optical chip. So, you observe the integrated optical chip on lithium niobate, and you have a laser diode to launch the light into the coil and a photodetector to receive the signal, and lot of signal processing will be done after this, electrical signal processing to analyze the signal and extract the information obtained from the gyroscope. So, we have various elements necessary for this operation. For example, you have to divide the function for input laser beam into 2 output ports. For example, at this point you have power dividers is needed, and there is a polarizer here. You can assume that there is a waveguide, on top of it you got a material which is very sensitive to direction of the electric fields of the light, and also you have a modulator here, phase modulator here. In a typical interferometric application, you know that the output light of the interferometer I output is in terms of cos square delta phi or delta phi by 2. So, that if you look at the input output relationship, cos square out. So, this is not very sensitive at these points. So, you need to bias the coil or the signal at 45 degrees points. That means periodically that is where the linearity, you require a linearity of the input output. For example, I will put delta phi on the y axis, or maybe light intensity on the y axis and the phase shift or the omega on the x axis. We need a linear response. So, in order to achieve a linear response, we have to bias this coil at some point like this. So, the biasing is equivalent to ramping the signal, the clock signal, so that you get continuously the light is biased at that particular point. So, ultimately what I want to say is that you need a modulator, maybe phase modulator you can call it. And also of course, all these are single mode waveguides. And also polarization has to be maintained, single polarization. So, there are several components necessary for a application like this, and they could be put in a small wafer like this. This is an important application. Similar application, similar situation arises in many other applications where you would like to process a signal based on some parameters, etc. So, optical techniques have proven to be very good, and if the entire thing is in the optical domain, you have a lot of advantages, and like a high sensitive sensors, etc. could be made using integrated optical devices. Of course, later on I will show you 1 or 2 examples where the optical signal itself, the chip itself is a sensor. In this particular case, we have the coil, fiber coil as the sensor, whereas we can have the device where the light itself will be sensed based on the input parameter. That example we will take up later on. So, finally, another popular application some time ago for the storage. So, storage is a very important function in engineering, particularly in electronics engineering. You need to store a lot of information before you can do the processing and so on. So, we have many types of storage devices like magnetic disks, then now flash RAMs and so on and so forth. So, optical techniques can provide very high data storage like the holography, holograms and so on can store a lot of information. In this particular example, I would like to briefly show you a disk pickup application. So, you have an integrated optic chip which can be used for reading and writing onto a optical disk. You have an optical disk here shown, and there are several like in conventional electronic memories, you have a lot of bits or storage locations which have to be written on or read out, and they have to be processed. So, you have a laser, this chip has got a grating, this is the crucial elements in this. You have a focusing grating and which can focus onto these bits very accurately, and it could be designed such that it can address any of these elements. The movement of the disc also could be arranged such that the bits are accurately aligned with the where the spot is focused. For this arrangement, we start with the laser diode as the source of the light, which is focused onto this grating. It could be directed by using other elements also if necessary. You can make another lens here. There is a lot of other you see that. Okay, let me start with this. You see the light is focused onto this grating in a planar way. This is a planar waveguide, and there is a relief grating here which can focus the light onto these bits, and the received signal also is received by this and directed into these output ports. So, there could be photodetectors here to convert the optical signal into electrical signal, and later on you can do a lot of processing at this point. So, what I am trying to show here is an integrated optical chip for disk pickup applications. So, we will take up more applications as we go along with it. These are applications with conventional integrated optical elements like the waveguides, gratings, prisms, lenses, and so on and so forth. In future we will think about components which are made on the optical waveguides themselves. Thank you very much for this module.